Hey everybody, this is lecture 23 of my Numerical Methods class. But hey, wait, if you're here as a calculus student, don't go. There's still going to be plenty here that you can learn about numerical integration. I'm calling this all you might ever want or need to know about numerical integration, for most people at least. Especially maybe if you're in AP Calculus and or are using this book by Hughes Hallett, you're going to see that a lot of the things that I talk about are emphasized in that book as well. It's the main kinds of things that you need to know. My class uses a more advanced book called Numerical Methods, Numerical Analysis in fact. Chapter 4 is all about numerical integration. We're only doing a very small part of Chapter 4 for my class because it's spring 2020, we have the coronavirus going around, it's a shortened semester. So I'm trying to emphasize the main things. We're going to go on to numerical solving of differential equations next. So here's the plan for lecture 23. We're going to look first of all at our main problem. That's the main problem for the entire lecture. We're trying to find an area under a curve, in other words a definite integral that we are interested in. It's a very important kind of definite integral. It's an area under something called the standard normal curve. The bell curve you hear it called sometimes as well. It's got tons of applications. For my students, we'll be reviewing what you may have learned about numerical integration in calculus. But again, I'm going to try to approach things at a pretty basic level, especially at first. Even if you're just learning this for the first time, I think you'll still get some benefit from it. So we'll talk about the 5 main rules you typically learn about in calculus. The left-hand rule, the right-hand rule, the trapezoid rule, the midpoint rule, and what is SIMP? SIMP stands for Simpson's rule. And we'll be approaching these things as Hughes Hallett does from an intuitive, you might say empirical perspective based on some data. For Simpson's rule, especially, the formula that we use at first is motivated by the nature of the errors in the different methods. We'll give geometric interpretations of all these rules, including Simpson's rule, using something called quadratic splines. Now, in lecture 22, I talked about cubic splines. Here in lecture 23, I'm going to talk about quadratic splines. We'll see an alternative formula for Simpson's rule, which is actually the way that I first learned it way back when. I will remind my students about cubic splines and how they can be used to integrate as well. And then finally, at the end, we'll do a theoretical thing. We'll talk about the error bound for Simpson's rule. All right, so here's our main problem. Page 1. Estimate the area under something called the standard normal curve over the unit interval from 0 to 1. So x goes from 0 to 1. Here's what the graph looks like. The formula for the standard normal curve you see is f of x equals 1 divided by square root of 2 pi times e to the negative x squared over 2. Looks like a bell-shaped curve. We're trying to find the area under this curve between 0 and 1. Why? Well, because this type of problem is super important. It has literally billions, if not trillions, of applications. And I'm not just talking possible applications. I'm talking maybe real applications that people have actually used this for at some point. Okay? Super important thing in applied math. Where is it used? Well, mostly in statistics and its applications, but of course statistics has billions and maybe trillions of applications. Normal curves show up everywhere. And not just the standard normal curve, lots of other normal curves, but they're all related to each other. You can do something called standardization to take an arbitrary normal curve and convert it to a standard normal curve. Statistics and its applications includes business, economics, engineering, and all the sciences, whether they're social or physical sciences. I'm going to show you 2 kinds of technology in this lecture. I'm going to show you some Mathematica, and I'm going to show you some spreadsheet stuff. Most of you will be able to do the spreadsheet stuff. Not many will be able to do the Mathematica, but I think it's worth showing anyway, both for my students and others who it might be useful for. So one thing Mathematica can do is it can tell you the probability density function for a normal distribution with a mean of mu and a standard deviation of sigma. If you don't know what that means, it's okay. The standard normal curve has a mean of 0 and a standard deviation of 1. It's the curve that I just showed you there. So there's the formula, if you didn't know it, that you can get from Mathematica. But of course, you can also look this kind of thing up on Wikipedia, for example. And then, for example, I can enter it into Mathematica and I can plot it, for example. And here's the plot that I just showed you in the PowerPoint. All right, so that's the first thing I wanted to show you in Mathematica. So let's go back to the PowerPoint now. And once again, look at our main problem. We want to find an area under a curve. Aha, that's a calculus problem. Okay, right? If you have done definite integrals, you know that they give you the area under the curve, at least if the curve is above the axis. Fundamental theorem of calculus to the rescue, FTC, right? So the answer must be that the integral of this function is what? What does the FTC say? Well, capital F of 1 minus capital F of 0, where what is capital F? It's an antiderivative of little f. Capital F prime equals little f. Sound good? Right? Isn't that great? That's always the way we do integrals, isn't it? But what is f? What is capital F? We know what little f is. What's capital F? You can spend your whole life trying to find capital F here as what you would call an elementary function in finite closed form, which basically means any kind of function you typically written down to this point in your life, unless you've done infinite series, but you will never succeed. And in fact, it's been proved that you will never succeed. Isn't that amazing? Somebody proved that it's not possible to find a formula for capital F as an elementary function, functions you're used to like polynomials, rational functions, roots, trig functions, inverse trig functions, logarithms, exponentials. You can't write it in finite closed form. Okay? Doesn't mean capital F does not exist. It just means you can't find an ordinary kind of formula for it. That's what it means. You'll never succeed in that way. So, what that means is we need to approximate the area in some way. We need to turn to our high technology computing, like a spreadsheet, like Mathematica, like a calculator, like Maple or MATLAB or R or Python, and approximate the answer. Or use low technology, a table of values that you can typically find in statistic books. Of course, we could take the easy way out and just use the technology, use pre-programmed technology to estimate the integral and therefore get the area. And we will be doing that in this lecture, so we know the more precise answer, the more accurate answer. But we want to understand where those approximations come from. That's the goal. This is a numerical methods class, or maybe you're in a calculus class. In numerical methods, numerical analysis, one major goal is to learn the math behind such program, how such programming is done. That's important. So we're going to begin by reviewing what you may have learned about in calculus, about numerical integration, or maybe what you were just learning about. Numerical approximation of definite integrals is what numerical integration is all about. All right, so let's do our review, or again, maybe this is new for you for the first time. What are we given? We're given a continuous function, f, defined in a closed interval. Now, actually, you can relax this condition of continuity. You could say it's got finitely many discontinuities, for example, that are jump discontinuities. That would be okay. But let's keep things simple. Assume it's continuous over the interval. It's got a nice graph that, in fact, also has maximum and minimum values as well. Then you choose a positive integer n, 1, 2, 3, 4, 5, 6, etc. That's going to represent the number of subintervals in our partition, our breaking up of the entire big interval from a to b. Then find what's called the step size, typically written delta x. That's going to be the length of the interval, b minus a, divided by the number of pieces, divided by n. Sometimes, if the variable is called t, this would be called delta t instead of delta x, but don't worry about it. And you can also find what are called the partition points. xi equals a plus I times delta x, which, since delta x is b minus a over n, you can also write like that, gives us our partition points, the endpoints of each of the intervals. Here's a picture of what's going on when n is 5, so we've got 5 intervals. A equals x0, and in fact, if you replace I with 0 here, you will get just a. When I is 1, you get x1. When I is 2, you get x2, etc. And the lengths of each of these subintervals is this thing, delta x. By the way, I will warn you later on in this lecture, I'm also going to label delta x with an h as well. That's a common thing to do in calculus. When n is 5, in this case x5, it is the same as b. If you replace I with n here, the n's will cancel, and you'll be left with a plus b minus a, which simplifies to b. Okay? Note, like I just mentioned, x0 equals a and xn equals b. Then you choose a method of approximation. Again, the standard methods are the left and right hand rules, the trapezoid rule and the midpoint rule, and this thing called Simpson's rules. There are actually other rules that can give you less or more accuracy beyond these. But these 5 are the main ones that most people might want or need to know, okay? So I'm limiting it to this, except a little bit with cubic splines on a couple slides later on. Then compute, implement the method. So you need to know how to use these methods. Now I've grouped these methods into 3 main groups. The left and right hand rules are grouped together. They are pretty similar to each other, and they have approximately the same absolute error when they are used. The next step up in goodness, you might say, is the trapezoid rule and the midpoint rule. They are better than the left and right hand rules in general for a given value of n. And they are of the same order in their errors. Actually, the midpoint rule we'll see is better than the trapezoid rule in general, but not by like a factor of 10 or something. And then the last best rule is Simpson's rule, we will see. Okay, and these build from each other. So what are the left and right hand rules? Both of these rules use what are called approximating rectangles. I am going to show you a graph here, but initially you might want to just imagine a graph. You've broken up the interval into a bunch of pieces. You're going to be using rectangles to approximate the area under the graph. You use appropriate endpoints in each case of each subinterval to determine the heights of the approximating rectangles. For the left-hand rule, for example, you use the left-hand endpoint of each interval, that's why it's called the left-hand rule, to plug into the function to find the height of the approximating rectangle. This f of xi minus 1 is a height of a rectangle because it's the height of the graph. Pretend the graph is always above the axis here. This stuff does apply when it goes below the axis, but we're only focused on trying to understand it in the case where it's above the axis. So that's a height, and this is a width. Height times width is the area of a rectangle, and then you're adding those up. You can use the summation, sigma notation, or you can write it out. Here, I goes from 1 to n, and you've got an I minus 1 there. So the first thing you plug into f is x0 when I is 1. 1 minus 1 is 0. Then when I is 2, 2 minus 1 is 1, so you plug in x1, etc. When I equals n, you plug in I equals n here, and you get an n minus 1 there. You've got n terms in the sum, giving you the heights of n rectangles. When n equals 2, for our example, f of 0 is 0.398942. F of 0.5 is 0.352065. You can check that. And in fact, I would suggest having your calculator out and checking some of these numbers as we go. And delta x in this case is 0.5. So I've taken the interval from 0 to 1. A is 0, B is 1, n is going to be 2. I'm going to take 2 subintervals, the first one from 0 to 0.5, the second one from 0.5 to 1. Then for the left-hand sum, I'm plugging the left-hand endpoint of each interval into the function to find a height of a rectangle. I'm going to show you a picture here in a minute. And these are the areas of those added up. And the approximation is about that. What about the right-hand rule? You use the right endpoint of each interval. Notice I've got an x sub I here instead of an x sub I minus 1. So in general, when I is 1, I plug in x1. Then I plug in I equals 2 here. And then at the end, I gets replaced by n. I plug xn into the function to determine the height. This is for n equals 2 again. This here is f of 0.5. This here is f of 1. My intervals, again, is from 0 to 1. x0 is 0, x1 is 0.5, x2 is 1. And delta x is 0.5. Here is the picture for both of these. Okay? So just take the time to look this over again. Once again, x0 is 0. x1 is 0.5. This is 0.5 here. And x2 is 1. Okay? And for the left-hand rule, notice over this first interval, we take the left endpoint at 0, we plug it into the function, we get the height of this rectangle, times delta x, which is 0.5, gives us the area of this rectangle. So this rectangle's area would be this product right there. And then for the second subinterval, from 0.5 to 1, the left endpoint is 0.5. We plug that into the function, we go up to the graph to get the height of the second rectangle. You see this point right there. This is the height of the second rectangle. You can see it over here as well. Take that height times the length of the base. That's going to be the area of that second rectangle. That's this product. You add those areas together, you get the total area of these two rectangles combined to give you an approximation to the area under the red curve. And you can see it's too big because the rectangles are above the graph. That's because the graph is decreasing. When your function is always decreasing over the given interval, the left-hand rule will be an overestimate. And that actually applies even if the graph goes below the axis. Okay? the left-hand rule will be too big. On the other hand, the right-hand rule, you can see when the function is decreasing, is too small. Over each subinterval, from the first subinterval is from 0 to 0.5, pick the right endpoint. That's why it's called the right-hand rule. In this case, pick 0.5, go up to the graph, and make that the height of your rectangle. So this rectangle has a height equal to this distance right there, and a width, once again, equal to 0.5. The area is this product right here. And the second rectangle goes from 0.5 to 1. Its right endpoint is 1. We go up to the graph right there to get the height of that rectangle, and the base is 0.5. This product gives the area of the second rectangle. You add those up to get about 0.297. For the right-hand approximation, you can see it's too small. When the function is decreasing over the entire interval, the right-hand rule will be too small. And again, that works even if the graph goes below the axis. Okay, so if the function is increasing, it gets reversed. You might want to take the time to draw that. If the function goes up and say is above the axis, you will see that the left-hand rule will be too small and the right-hand rule will be too big. That's good to remember. You may even want to pause the video and write those things down. All right, on to the trapezoid rule. It's called the trapezoid rule because you can interpret it in terms of approximating trapezoids. It's also the average of the left and right-hand rules. You saw with the previous example, the left-hand rule was too big, the right-hand rule was too small. Maybe we should try averaging them, add them together and divide by 2. And that's one way to think about the trapezoid rule. And that's the way I'm thinking about it here. And this is the way that you'll find it in Hughes Hallett's calculus book. 1/2 of left plus right, or left plus right all divided by 2. It's the average of the left and right. In this case, it gives you about 0.336261. You can double check. All right, so that's one way to do it. And that is sort of an empirical thing here. This seems like a reasonable thing to do. It's based on the data, based on seeing that the left-hand rule was too big and the right-hand rule was too small. Maybe by the same approximate absolute errors. It's not exactly right, but maybe approximately. So why not average them? Maybe that would be better. You can also write this in terms of summations. You can plug in the formulas for the left and right in terms of summations and multiply the 1/2 through both to get this here and this here. And then you can combine those summations together to say you're summing the product of these averages times delta x. Then you can write that out. And you can also simplify. And if you simplify and factor out the common factor of delta x over 2, you can write the formula for the trapezoid rule in this way. And that's the way that I learned it way back when, actually. Okay, you might want to double check that you get the same thing. When the case when n is 2 again, we do get the same answer as before, about 0.336261. Here's a picture of what the trapezoid rule looks like in this situation. And it is essentially adding up the areas of these two trapezoids. The area of a trapezoid is the base times the average of the heights. So for example, this product right here, delta x is the base, that's 0.5 right here. F of x0 plus f of x1 divided by 2, that's the average of these two heights. The f of x0 is the height of the left side, f of x1 is the height of the right side. You average them, you get the area of the trapezoid. Okay, you can also break down a trapezoid into a rectangle and a triangle. You might want to confirm you get the same area that way. You can see, well, we get about 0.336, and you can see the area under this, the area of these trapezoids gives an approximation that's too small, right? Because there's some area that's missing here, and you can't quite see it so well here, but there is some area that is still missing. Because the graph is concave down, the trapezoid rule is going to be too small here, okay? Because the graph is concave down. That actually applies even if the graph is below the axis, though it's harder to visualize. The trapezoid rule will be too small. It will give you an underestimate when the graph is concave down. That's something you may want to write down. On the other hand, if the graph is concave up, whether it's above the axis, below, or both, the trapezoid rule ends up being too big. Okay? With the trapezoid rule, the tops of the trapezoid in this picture are really secant lines to the graph of this concave down function. By the way, the function does become concave up if we go further to the right, the normal curve. But for this interval from 0 to 1, it's concave down. So if it's concave up, though, the trapezoid rule is too big. If it's concave down, the trapezoid rule is too small. Here's another rule. It's called the midpoint rule. Uses approximating rectangles again, back to rectangles. But we use the midpoint of each subinterval to determine the heights of the rectangle instead of the left or right-hand endpoints. So in general, the formula can be written this way. There's the height of your, there's the width, excuse me, of your approximating rectangle. And look at this, f of the average of the x's, the partition points. That's plugging in the midpoint of each interval into f to determine the height. And you can, of course, then write it this way and factor the delta x out if you like. And for our example, when n is 2, you get this. This right here is f of 0.25. This is f of 0.75. 0.25 is halfway between 0 and 0.5. It's the midpoint of the first interval. 0.75 is halfway between 0.5 and 1. It's the midpoint of the second subinterval. In the end, you get about 0.3439025. And here's the picture. Okay? So once again, the midpoint of the first interval is 0.25. That's what I'm trying to emphasize here. Plug 0.25 into the function. The second coordinate of this point will be f of 0.25. That determines the height of this rectangle. The base is 0.5 still. The height is this distance, which is f of 0.25. The other rectangle, you take 0.75, which is right there, and plug it into the function to get this height right there. Okay? It's not so clear in looking at this whether this approximation is going to be too big or too small. However, it will be too big because the graph's concave down, we will see here in a second. So remember, for concave down graphs, we saw the trapezoid rule was too small. I'm claiming the midpoint rule here is too big. What is the relation of the midpoint rule to the nature of the function? We can see it if we rotate the top of the approximating rectangles about their midpoints until they become tangent lines. Here's a visual of that. I made an animation. Notice we take the original rectangles and rotate them about their midpoints until they become tangent lines. Do they really become tangent lines? Are they really tangent to the curve? You can verify that. Is the area still the same? Is the area of the final trapezoid in fact still the same? It is, because you're rotating around the midpoint. If it's the same as the area of a trapezoid rule, why don't we call this a trapezoid rule? Well, because we don't want to get it mixed up with the other trapezoid rule. And at its most fundamental level, it's better to think of it as a midpoint rule. But this helps you see, helps you believe that when the graph's concave down, the midpoint rule is going to be too big. The trapezoid rule is too small. The midpoint rule is too big when the graph is concave down. It flips again when the graph is concave up. Then the trapezoid rule would be too big and the midpoint rule would be too small. When the graph's concave down, the tangent lines are above the graph. And in the case where the graph is above the axis, that's what allows you to see the area is too big. Yes, for a concave down, mid of n is too big. Take a breath here. All right, I'm also going to get a little drink here. We're trying to work our way now towards Simpson's rule. And I want to approach Simpson's rule empirically. Again, that's what Hughes Hallett does, the calculus book. To accurately see, how to derive Simpson's rule, what we want to do is we want to accurately approximate the errors in these approximations. Though to do so, we need to cheat and use technology to see that in reality, the best sixth place after the decimal approximation to this integral is 0.341345. You may want to write that down if you don't have technology to check that, or if you do have technology, like your calculator, go ahead and check that. 0.341345 is the best sixth decimal place approximation to the integral. Since error in an approximation is always the actual value that you want to approximate, the integral in this case, minus the approximate value, and I always remember this by going in alphabetic order, AC comes before AP, we can make the following table that summarizes what we've seen so far. So n is 2 in each case. We've seen these approximations for the left-hand rule, the right-hand rule, the trapezoid rule, and the midpoint rule. Again, the actual value to 6 places after the decimal is this 0.341345. So taking actual value and approximating or subtracting the approximate value in each case gives you this error, which can be negative or positive. It's confusing. Negative errors actually result from approximations that are too big. Careful. And positive errors result from approximations that are too small. It's a little confusing, but it is the way things are done. And there is a good reason for that I'm not going to get into. So the error does have a sign, positive or negative. If the approximation is too big, the error is going to be negative. If the approximation is too small, the error is going to be positive. Though you can talk about absolute error, where you take the absolute values of these errors and get rid of any negative signs then, and these are all positive. Okay? Notice that trap and mid, in terms of their absolute errors here, are about 10 times better, on the order of 10 times better than left and right. Okay? If you take the left and right errors, absolute errors, and divide them by 10, you don't get the errors for the trap and mid, but it's in the ballpark. That's what I mean on the order of. Okay? On the order of 10 times better. Also, mid of 2 is on the order of 2 times better than trap of 2. This number is about half as big as this number. Twice as close to 0. Okay? That's worth writing down and remembering for the future here. What else do we want to see here? These kinds of observations that I just made from the previous slide hold as n increases as well. Forgot to say left and right are on the same order of each other. You know, these absolute errors are in the same rough ballpark of each other. That continues to hold when n is bigger. And it's 4, 5, 10, 20, 100, 1,000. It still continues to hold. And the other observations still hold too. Trap and mid are about 10 times bigger than left and right. If you know the left and right errors for a particular value of n, you can divide them by 10 to get the approximate absolute errors for the trap and mid. And once again, mid's about 2 times better than trap. We also want to see what happens as we, for example, double the value of n. So if I double n from 2 to 4, what happens to all these errors? You could take the time to double check. This would take some time for you to do. That left of 4 is this, right of 4 is this, trap of 4 is this, and mid of 4 is this. That might be worth you taking the time to do. It probably will take you 10-15 minutes to do if you want to pause the video and come back. The errors do get closer to 0. They stay the same sign. It's still the same function. It's still decreasing in concave down. So left is going to be too big and it's going to have a negative error. Right is going to be too small. It's going to have a positive error. Trap is going to be too small and it's going to have a positive error. And mid is going to be too big and it's going to have a negative error. The errors did go down. We'll talk about how much. Also notice the absolute errors for the left and right are on the same order of each other. They're close together, though with opposite signs as we saw over there. Trap and mid are on the order of, not exactly, but on the order of 10 times better. They're even more than 10 times better actually when you look at these numbers. If you divide these numbers by 10, you get in the rough ballpark of these numbers, very roughly. More precisely, mid is pretty close to half the error as trap. It's twice as good. And how much did these absolute errors go down when n doubled from 2 to 4? Need to go back to the other slide again. For trap and for left and right, the absolute errors are on the order of something times 10 to the negative 2. And these were something times 10 to the negative 3. Here, well, we still got something times 10 to the negative 2, I guess, and then also times negative 3. So I guess what I meant to say, focus on more, is that actually, when you double n, these errors get cut in half, whereas these errors get cut by a fourth. Keep track of these numbers, close to 0.04, say, for the left and right. These numbers here are close to 0.02. They got cut in half. On the other hand, for the trap and mid, these numbers, well, this one's close to 0.005 and this one's close to 0.0025. These numbers are approximately 1/4 as large. Now note that the errors for left and right are on the order of half of what the errors were when n was 2. When n is 4, the errors are half of what they were when n is 2. And for the trap and mid, when n is 4, the errors are on the order of 1/4 as big as they were when n is 2. Okay, that takes some thinking. Maybe you want to rewind and listen to that again, look at the numbers again to hear what I was saying. That's probably the hardest part of what we've done so far, to see that. The fact that the mid is on the order of twice as good as trap, meaning the error is twice as small, that gives motivation for the following version of Simpson's rule. This is the empirical approach as a weighted average. And again, that's what Hughes-Hallett emphasizes. What's a weighted average? We're going to add some numbers and divide by how many there are. Essentially, we're going to add mid twice and trap once, and think of that as three numbers, so we're going to divide by 3. There we go. Simpson's rule for a given value of n is 2 times the midpoint rule plus the trapezoid rule divided by 3. In other words, mid n plus trap n, 3 numbers added, divided by how many numbers there are, 3. I'm giving mid twice the weight because it does twice as well. The error is half as much as with the trapezoid rule. So this again is the empirical approach to Simpson's rule. It's not the way that I learned it way back when, but we will see the way I learned it way back when here in a bit. This definition, if you use it, leads to the following values for Simpson's rule. When n is 2 and when n is 4, you get these two approximations that are pretty close to the values, the true value. Here is more decimal places for the true value, to 8 places after the decimal, and then subtract those approximations. You get negative errors because these approximations are a bit too big. It's not clear why. And these errors are certainly close to 0. Their absolute values are very close to 0. Simpson's rule is doing very, very well, even with small values of n. Imagine how well it does with large values of n. And when n increases from 2 to 4, when n doubles, it causes the error in Simpson's rule to go down by a factor of 1 over 2 to the 4th, which is 1/16. This number you could check is about 16 times smaller than this number. Take this first number and divide by 16, you get in the ballpark of this number. Not exactly, but in the ballpark. So doubling n caused the error to go down by 2 to the 4th, down by a factor of 16. That kind of observation generalized. If you tripled n, from 2 to 6, for example, the error would go down by a factor of 3 to the 4th, which is 81. If you multiplied n by 10, if n went from 2 to 20, the error would go down by a factor of 10 to the 4th. It would be 10,000 times smaller. Wow, that's pretty cool. You may want to write that kind of thing down. All right, what's the geometry of Simpson's rule? We've talked about the geometry of the left and right-hand rules, trap and mid rules. Is there some geometry to Simpson's rule? Can we geometrically interpret it? The answer is yes, but it's harder. The way to do it is in terms of quadratic interpolations, okay, and also splicing together quadratics to make what you could call quadratic splines. Again, in lecture 22 with my class, I talked about cubic splines. Quadratic interpolations over each interval. For our example, that would be the interval, first of all, from 0 to 0.5, then from 0.5 to 1. We're also going to use the midpoint of the function value and the function value there as a data point as well. So now, it's kind of like we're combining the data points, the nodes, for the left, right, and trap with mid. Right? The nodes that we use for the left, right, and trap rules are 0, 0.5, and 1. The nodes we used for the midpoint rule, the sample points, so to speak, were 0.25 and 0.75. We're going to combine those numbers with Simpson's rule, really, to get 5 data points. x0 is 0, x1 is 0.25, x2 is 0.5, x3 is 0.75, and x4 is 1. And the new delta x for Simpson's rule, which we'll call h, ultimately is 0.25. Okay? Let's go back to n equals 2 and focus on that first subinterval from 0 to 0.5. We're going to use 3 nodes, 0, 0.25, and 0.5. We'll label them. This is a new labeling now. x0 is still 0. x1 is no longer 0.5 here. It's going to be 0.25. And x2 is 0.5. We're focused on that first subinterval of the original partition. What are the function values at these 3 points? You can double check, plugging them back into f, our standard normal curve function. Again, that's 1 over square root of 2 pi e to the negative x squared over 2. You can double check that you get these numbers. F of 0 is about that, f of 0.25 is about that, and f of 0.5 is about that. The simplified interpolating polynomial and its integral, which is doable by hand, turn out to be what I'm about to show you here. You probably would not want to compute these without technology. Well, my students should be able to. If you're just a calculus student, not in numerical methods, you're not going to know where this is going to come from, okay? I will show you Mathematica can compute these things, but you're not going to know where this comes from. P1 of x, you can see is a quadratic function. Just try to get the main idea here. It's a quadratic function. Highest power of x is x squared. Its coefficient of x squared is negative, so it's a concave down graph. Its slope at 0 is this number. Its vertical intercept is that number. Turns out this is a polynomial function, a quadratic, that very well approximates f of x on the interval from 0 to 0.5. And so if you integrate it, it should be close to the value of the integral of f on that interval from 0 to 0.5. Here's the value of the integral. Mathematica can compute this thing. I do want to show you this stuff on a spreadsheet too, by the way. I wanted to do it earlier, but I've forgotten. Let me show you Mathematica can compute those things there. For my students' sake here. Yeah, to get the interpolating quadratics, I want to emphasize for my students that interpolating polynomial can be used in this kind of way. And we can approximate it with n. There is the first interpolating polynomial. And in fact, we can see the numbers there and we can integrate it. We can numerically approximate the integral of the function to get this number that's about 0.19 that we see here in this slide. Okay, so I'm using Mathematica there. Again, for other people's sake and my students, I want to show you this stuff on a spreadsheet as well, just not right now. I think I'll save the spreadsheet for the end. Okay, and if you're most interested in the spreadsheet, maybe you want to jump to the end. For the second subinterval, from 0.5 to 1, we relabel the nodes to be x0 equals 0.5, x1 is 0.75, and x2 is 1. The corresponding function values of the original function f are now these numbers. So this number is f of 0.5. We actually already saw that number in the previous slide. We're reusing it here. This is f of 0.75. This is f of 1. Turns out the simplified interpolating polynomial and its integral turn out to be these numbers. When I say these integrals are doable by hand, I mean you literally could integrate this thing by hand even though it wouldn't be pleasant. Notice this integral is from 0.5 to 1. Therefore, to get the approximation to the integral over the entire interval from 0 to 1, we need to add the approximations from 0 to 0.5 and from 0.5 to 1. And we get this number, which is the same number we got with Simpson's rule when n was 2 before. Yes, this was when n was 2, even though now we're using more subintervals when we piece together these quadratics in a quadratic spline. And it is the piecing together of P1 and P2 that you would call a quadratic spline if we defined a piecewise function. P of x to equal P1 of x when x is between 0 and 0.5, and P2 of x, this function here, when x is between 0.5 and 1. That's a splicing together to create a quadratic spline. It's the integral of that entire piecewise function over the interval from 0 to 1 that we are approximating by adding the integrals over the pieces. And again, this is the same number we got before, 0.3143555. Okay, so it is giving us what Simpson's rule gives us. Here's a way to visualize it. Each green curve that you see here is actually a parabola, and by each green curve I mean over each piece. This first piece right here, when x goes from 0 to 0.5, and a second piece when x is 0.5 to 1 there. And those are two parabolas that are not the same parabola. They're separated at this point here. They look like they could be the same parabola, but they're not. This one you can definitely see has more concavity than this one. This one's pretty straight. The x squared term is pretty small over there. But they are giving us, by integrating them both and adding them, the value of Simpson's rule at 2. And they're so close to the graph of f, which is red, so close you can't tell the difference. It's not matching up with the red graph exactly. And in fact, we saw it's giving us an area ever so slightly too big. But you can't tell the difference really, for all we can tell with our eyes. All right, here's an alternative formula for Simpson's rule that my students should know and other students may want to know. And this gets at the way that I first learned it way back when. Keep saying way back when. How long ago was way back when? Well, I'm not going to tell you. This derivation is kind of a pain to do by hand. I will show you Mathematica can do it. Consider the case of three equally spaced nodes. So we're focusing on one of the subintervals here. So we got an x0, x1, and x2 here initially. We're just focused on one subinterval. Take x0 to be A, x2 to be B, not necessarily the original B. Talking about a smaller subinterval. I'm talking generally here about some interval that I'm really just breaking up into two pieces. Though in terms of left and right hand rules, it would be just one piece. And same with midpoint and trap. And x1 is the midpoint. So again, I've got three nodes. x0 is A, x1 is the midpoint, and x2 is B. The Lagrange interpolating quadratic polynomial takes the following form. My students have seen this before. If you're a calculus student, you probably haven't. Don't worry about this. This is just a special way of coming up with a quadratic function, a parabola graph that's going to go exactly through these 3 points at x0, x1, and x2, and the function values there, f of a plus b over 2, and f of b that you see here, here, and here. But will not necessarily match the function at other points, but will approximate it. Okay, so like I said, if you're a calculus student, don't worry about this. You could think about why this would work. Why is this going to go through the 3 points exactly? And what is h here? H is delta x. Okay? H is delta x. Expanding this function, this quadratic, out and integrating it with some pain can be shown to give you this. It gives you this initially, and I'll show you this on Mathematica, which can be simplified to this. And for one interval broken up into two pieces, x0 is A, x1 is A plus B over 2, and x2 is B, this is what Simpson's rule gives you. And this is the way that I initially learned it. And it does give us the same answer as before. Based on data from 2 slides ago, when we were looking at the interval from 0.5 to 1, we could have done from 3 slides ago and look at the interval from 0 to 0.5. We got the same 0.14988 that we got on the slide 2 slides ago. Actually, it was more than 2 slides ago. Oh, that was a typo. Right there, 0.14988. Mathematica can do the algebra to simplify this for this integral. It puts a negative sign in there for some reason, but you can get rid of that negative sign by realizing that a minus b is really negative 2h. So, and since you're cubing it, you can get rid of the negative sign and write this as 2h quantity cubed. And that's what I have. Let's see right here, you see a 2h quantity cubed over 24h squared you see down there, and here you see the f of a plus 4 times f of the midpoint plus f of b, which is what you see here. So you get this funny 4 in here, is kind of the point. It's kind of a weird formula. h over 3, which is again is delta x over 3. Where h for one of these smaller intervals is really going to be 0.25 instead of 0.5. F of a and f of b get added, and then 4 times the function value at the midpoint. Again, it's kind of strange, but that's what the formula becomes. It does give us that right answer. But in general, you have to add together things like this. Over a big interval, say, from a to b, broken into n plus 1 equally spaced nodes, x0 through xn, where n is even. Okay? So for our bigger interval from 0 to 1, we're thinking about breaking it up to x0 is 0, x1 is 0.25, x2 is 0.5, x3 is 0.75, and x4 is 1. N is 4 in that case. N is even, which really means n plus 1 is odd. You've got an odd number of nodes because you start with x0. Simpson's rule can be derived in this more general setting by adding up the formulas from the previous slide for the individual quadratics over each of these subintervals. And when you add those up, the multipliers of 4 times f of x1, and then 4 times f of x3, and 4 times f of x5, etc. need to be in there. F of x0 and f of xn need to be in there by themselves, but f of x2, for example, occurs twice. One for each separate interval that it is by. You know, x2 is the right endpoint of this interval and the left endpoint of this interval. So f of x2, for example, gets multiplied by 2. And f of x4 gets multiplied by 2. And f of x6 gets multiplied by 2. So now you get an even crazier formula. But it is the formula I learned. H over 3, which could be written as delta x over 3. For our example, h is 0.25. F of x0 plus 4f of x1 plus 2f of x2 plus 4f of x3, etc. You'd be down to 2f of xn minus 2 plus 4f of xn minus 1. And finally, you'd have f of xn. Okay? For my students, there are going to be other interpolation-related rules you can find in section 4.3. But I, in this shortened semester, am not going to require you to know them. Okay? But this is the one we're going to use. Besides, you'll see the trapezoid and midpoint rules in that section. In our example, again, for the whole interval, x0 is 0, x1 is 0.25, x2 is 0.5, x3 is 0.75, x4 is 1, h is 0.25, you get the same final answer, 0.3413555 as before. And you may want to double check these calculations if you believe these numbers. Okay? Take a breath, take a drink, we're not done. This is like, you know, everything almost everybody would want to know. We've got a bit more to do. We are going to come back to the error for Simpson's rule at the very end. But as a brief aside, I want to talk about integrating cubic splines. For my students, lecture 22 is partially about cubic splines. And Hermite polynomials focus on cubic splines. If you don't know about cubic splines, or for your calculus student, it's still good to learn a little bit here. I'm just going to give you the big picture idea of it. So what we're about to do is find what's called a two-piece clamped boundary cubic interpolation of the original function. Same function, standard normal curve, over the interval from 0 to 1. Two-piece means we're looking at the two subintervals, 0 to 0.5 and 0.5 to 1. Clamped boundary means we're setting the derivatives of our cubic splines, where we're piecing together two cubic functions. We're setting the derivatives at the endpoints equal to the derivatives of f at the original endpoints. So we're clamping the slopes, so to speak. Cubic spline takes the form as a piecewise function. S0 of x over the first piece, S1 of x over the second piece. Okay, standard notation to use here. S0 of x and S1 of x are going to be cubics, different cubics. Just like we pieced together two quadratics over the two separate intervals to get Simpson's rule, now we're piecing together two cubics over the separate intervals to integrate a cubic spline. Does that correspond to some higher order Simpson's rule? Well, I'm not going to say. Maybe, maybe not. I'll let you look into it if you're interested. Notice we've got two cubics here. Written in different forms, these just are two different convenient forms. This one over the first interval that contains 0, and when we plug in x equals 0, it simplifies nicely, as well as its derivative simplifying nicely at x equals 0. This one over the interval from 0.5 to 1 simplifies nicely at the left endpoint, x is 0.5. Also, its derivative simplifies nicely at 0.5. Based on these conditions, these are our conditions to solve ultimately for the a's. The a's, b's, c's, and d's, I should say. We want the function values to be equal at x equals 0. When you plug in x equals 0 into this, it simplifies to a0. So a0 must be 1 over square root of 2 pi. The value of this first one at the right endpoint must equal the function value there, so you get this equation. You may want to approximate these things here. I'm just going to let Mathematica do it. We want the derivative values at the left endpoints to match, and at the midpoint 0.5 to match, and you want similar kind of conditions on S1. Function values over the second intervals and derivative values over the second intervals need to match. Second interval. What you get is a system of equations. 8 equations and the 8 unknowns, A0 through D0 and A1 through D1, that you can solve. You don't want to solve such a thing without technology. Let me show you that Mathematica can solve it. Don't worry about the syntax here. It's solving. It's crazy looking exact answers, but we can numerically approximate those to get these numbers. And then I'm defining a piecewise function in Mathematica using those numbers. What's the integral of that function? It's about 0.341302, very close to the true value of the integral, even here with just 2 pieces for the cubic spline. Okay. Here's a plot of the cubic spline with the original graph, spline approximation. It is in 2 pieces. These are now both cubics instead of quadratics. I've got that graph on here as well. The approximation is 0.341302, very close. The error is 0.000043. The approximation is a bit too small, actually. And here is the spline approximation. You can't really tell if these are cubics, but they are. Cubics constructed to match the function values at the nodes as well as the derivative values of the nodes. And the derivative value there for both pieces matches up. All right, now we're on to our last couple slides, and then we'll look at a spreadsheet. This is more theoretical. We're looking at the idea of an error bound. In particular, let's do an example of an error bound for Simpson's rule. There are other error bounds as well. These are derived from Lagrange interpolation. My students know about that from the beginning of chapter 3. And theorem 3.3 on page 109 in section 3.1, but I'm not going to go through the derivation. Assuming the fourth derivative of f exists and is continuous, you can say that the absolute value of the error, actual value minus approximate value, in absolute value, the absolute error is bounded by less than or equal to this expression here, h to the fourth times b minus a, all divided by 180, times the maximum value of the absolute value of the fourth derivative of f. Okay, so kind of crazy here. Keep in mind, think about our example here to help you understand. For our example, a is x0 is 0 and b is 1 for the entire interval, so b minus a is 1. H, when we applied Simpson's rule with n equal to 2, was actually 0.25. Okay, and that was 1 over 2 times n, where n is 2. What is the maximum value? Well, you'd have to actually take the fourth derivative and find its absolute value. I would not try that without technology. I did use technology, I used Mathematica, I'll show it to you here. So for example, take h to be 0.25, take b minus a to be 1, and this simplifies. I have 0.25 to the fourth, that's h, divided by 180. You see the 1.196827 in here. What is that? That is the maximum value of the absolute value of the fourth derivative of the function. And this simplifies to about 0.0000260. Before we look at the graph, let's compare that with the actual error that we get by having Mathematica compute the actual value of the integral to that many decimal places. The actual is smaller. It is 0.0000108. Okay, a little bit more than half as small. So the error bound just gives just what it sounds like, an error bound. The actual error will be less in absolute value. Let's go ahead and see where I got the 1.19 with Mathematica here. So here I graph the absolute value of the fourth derivative of the function. This is again is the standard normal distribution. In absolute value, its fourth derivative you can see is maximized at 0. What is the value of that fourth derivative at 0? It's this, but we want to approximate that. It's about 1.19682, and then I rounded up to 7 in that last spot, which is what you see right here, 1.196827. Okay, so I'm applying this theorem assuming I got that graph. What my students should be able to do from this, though, is find minimum values of n to guarantee that the absolute error is less than or equal to some fixed value. This is the final slide, then we'll again look at the spreadsheet. What is the minimum value of n to guarantee, at least according to the theorem, that the absolute error in other words, the absolute value of the actual value minus the approximate value, is less than or equal to whatever number you want. I picked 10 to the negative 10. To do this, we need to find the minimum value of n, again, n is a whole number, 1, 2, 3, 4, 5, 6, etc., such that this is true. What did I do? I used the error bound theorem. I went ahead and used that value, 1.196827. That's the maximum of the absolute value of the fourth derivative. I divided by 180. Remember, b minus a is 1. This is h to the fourth here. 1 over 2n is the value of h. Think about the example. With the example, n is 2, so we have 2n plus 1, 5 nodes at 0.5, 1, or excuse me, 0.25, 0.5, 0.75, and 1. Okay? N is 2, 2n plus 1 is 5, so 2n is 4. 1 over 2n would be 1/4 or 0.25. This is 0.25 to the fourth. I essentially need to solve this inequality for, for n. That's certainly possible to do algebraically. I'll let you try that on your own. What you should get is n needs to be at least 46, greater than or equal to 46, according to the theorem. That really means we have 93 nodes, and h is 1 over 92, which is about 1.01087. Now we can actually get away with a smaller value of n. We can actually get away with n equal to or greater than 37. Let's confirm these things with Mathematica as well. So here's Mathematica's way of solving that equation for n, and it turns the positive root to be 45.1502. I'd want to round up to the next nearest whole number, so that's why I picked 46. Certainly the absolute value of the error when n is 46, like you see here, is indeed less than 10 to the negative 10. But it even works when n is 37. That's still less than 10 to the negative 10. But when n is 36, now that's an error bigger than 10 to the negative 10. All right, now we end with a spreadsheet, which is technology you all have access to. Let's go ahead and think in terms of the basic approach back at the beginning. So we're going to think about the left and right rules and midpoint rules based on a partition 0.5, 0.5 to 1, and particular sample points. We will compute the trapezoid sum as the average of the left and right. We'll compute the Simpson's rule sum as the weighted average of mid and trap, giving mid 2 times the weight. But I'll also compute Simpson's rule with that other rule that I showed you. To get the values of the function in here, notice the function is up here. I could type exp, for example, to start with, for the exponential function, to the negative x squared. X is in cell B4 here, so I can type that. I need the negative sign out in front of parentheses like this to make sure the spreadsheet does it right. Divided by 2, that's e to the negative x squared over 2. But I also need to divide by square root of 2 pi. I can type that like this, equal sqrt 2 times pi, use parentheses like this. That will compute the value of the standard normal distribution when x is 0. And then if you copy and paste this, it will update it correctly at the other values, because what happens is the B4 gets changed to a B5 here, then a B6, then a B7, then a B8. That's the way spreadsheets work. It's going to be handy to multiply those numbers by 0.5, 0.5 representing the original delta x. So I go ahead and get these values. All right, now this is a little bit fun as well, because what we can do here for the left-hand rule is we can add equals D4 plus D6. And if I copy and paste this down in the order that I have for mid and right, for the middle it'll get updated to equals D5 plus D7, which is the right thing to do. And for the right it'll get updated to equals D6 plus D8, which is the correct thing to do. That's again the way spreadsheets work. As I copy and paste the formula downward, the cell references get updated appropriately, as long as you don't use dollar signs for fixed cell references. The trapezoid rule, again, is the average of the left and right, so I can do equals C10 plus C12, all divided by 2, use parentheses like that. And finally, Simpson's rule is a weighted average, equals 2 times the midpoint rule, which is in cell C11, plus the trapezoid rule, all divided by 3. And there is our value for Simpson's rule, 0.3413555. Let's also double check the other way that I showed you, where we have h over 3, remember h is 0.25, over 3 times the sum, first the value of f of 0, plus 4 times the value of f of 0.25, which is x1 when we have the bigger number of nodes, when you have 5 nodes, plus 2 times f of 0.5 plus 4 times f of 0.75 plus back to just f of 1 without a 2 or a 4. Okay, that was the rule that I showed you with Simpson's rule, the alternative formula, and it does give the same answer. Yay. Okay, so that's the end of this video. Thanks for watching.